Hey there, math fans. You ever heard of a catenary? It's a shape that most people haven't heard of. I've encountered it a few times, and then a few years ago, I realized it appears everywhere. And then more recently, it came up again in a student project. I'm thinking of it because it came up in a homework question, this little cable going on here, and the student's asking about this. And this video is not going to help you. I'm sorry. I'll have to follow up with a separate video to actually do the math. But the point is, you actually see these everywhere, a hanging chain. Now, it's easy to assume, if you've never seen this, that a hanging chain is a parabola. It's pretty close to a parabola. It's a pretty good approximation. But a hanging chain is not a parabola. It's a different shape. So that's pretty amazing, and I'm going to show you several things here. So it's this shape. It's this shape. When they made the gateway arch, they made it a catenary upside down. When you look at the vacuum tubes on the wall of my house, that's a catenary. If you look at that lay hanging around my neck, it is. So how do we define it? What is it? Well, it's something you improve with physics about tension in a wire under gravity. And if all things have to balance out, you can't have unequal tension, because if you have tension higher in one spot, then it would just stretch more. So it has to all balance out. And that was proven in 1691, the beginnings of calculus. And it turns out to be related to the exponential function, so there is a nice thing about it. But I just want to give a few other examples. So here's a lay. I was trying to look for things around my house. So I found the vacuum tubes. But let me show you something here. So here's this. This is the shape. That's a catenary. All right, and there's the fool wearing it. And let's see if we can find another one here. Ready? This is a catenary. That shape, that hanging rope there. I unfortunately did not make it on the first try. It took me several tries. But I eventually got in there. Catenary? Yeah. All right, so those are some shapes. Let's get that out of here. And so I wanted to say a few things about this of interest. So first, here it is. This is the catenary shape. It's interesting to kind of play around with. It's between e to the negative x and e to the x. So if you know what exponential growth looks like and exponential decay looks like, it's like halfway between them. So anyways, that's that curve. But it's restricted. It can actually you can adjust a little parameter, and it looks like this shape. So given 2 points, you actually have more than one catenary that fits through it. But I drew the parabola that hits it at 1, 1, and you can see, especially as you get further out, they're different shapes. Now, if you're just looking at something hanging nearby, they're pretty close. But in the long run, they're a little bit different. So I always like to do a physical model. So here's that lay. Let's zoom in. There's the lay. Let's make this a little bigger so you can see it better. And I thought I would try to change my parameter to make it match. Ooh, so you can see the blue does a little better. A hanging chain is a catenary. The purple was the parabola. So there's our little example. I also thought, well, if I'm going to do that, let's do the other one. So here's the hanging rope. I turned it so that it would sort of match up. Let's see if we can hit that hanging rope from my other example. I made it, so I zoomed in so you could see it. Now in this case, when I draw the parabola, it's really indistinguishable. Okay. But anyways, it was proven from these physical behavior of if something's hanging under gravity and the assumption is that the tension is equally spread out, it leads to this shape. So that's kind of interesting. Well, the reason I find it even more interesting is I came across a fact I hadn't encountered before, and I want to grab it here and show it to you. It's a fact about minimum surface area. We have somebody in our department that does research on this, Jonathan Zhao, but it's soap bubbles. So if you take two rings and dip them in water and then pull them apart, it turns out that the soap bubble minimizes tension, because if it doesn't, it pops. So that's really interesting, I thought. But it was proven by Euler, and yes, Euler did prove this is minimum surface area in the 1700s, what shape this has to be. And it turns out not to be a cylinder. A cylinder does not minimize surface area, which is a whole different discussion that I've had students get frustrated with me about. So if you take two rings like this, I've got a little visual ready, because I've made this for several students doing projects on this thing, and you draw that cylinder, that is not the minimum surface area that connects those. It really bothers people. That's because when you're in the middle, if you could make it skinnier, your circumference would be a lot less. There's a balancing act that happens. That shape is a catenoid. Catenoid is a catenary revolved around. It's super interesting, I think. That's the minimum surface area. The blue is less surface area than the green. It really bothers people. But that is, maybe it doesn't bother you, but I've had students really debate about this. And so I have made a project where they just computed the surface area of both and found out, yep, indeed it is different. Okay, so let's show Jonathan's video here. Let me pull it up and get it ready. So here you go. Let's just watch it. As you pull it apart, it looks kind of like a cylinder initially. But then as you look on the edge there, that's a catenary. And as you pull further and further apart, eventually pops. So catenary has this restriction that it can't go beyond a certain amount. Okay, let's finish this. That's it. If you do look, I hadn't seen this before, but if you look at a suspension bridge, that's also a catenary. But if there's weight, like it's physically attached to the weight of the bridge itself, then it's more of a parabola shape. So the Golden Gate Bridge suspension wires, because they're under strain, is more of a parabola. That was interesting. But the little bit of history I got was, yeah, they proved this in 1691. Euler then proved the catenoid was minimum surface area. Catenary means chain, so it literally means hanging. I guess Thomas Jefferson was the first to use it kind of in the English language because he read a paper about someone proving something about this. All right, so there's a bunch of history. There's a lot of curves out there that you haven't encountered. I can tell you many, many more, but this one you see everywhere, so I thought it was worth saying something about.